Nuclear chemistry. Or is it nuclear chemistry? Nuclear or nuclear?
Nuclear.
Nuclear. That's the right way to use the vocabulary word, and that's what we're about to do. Use about 20 of them, right, Milty?
20.
There you go.
First one.
Hit me with the definition, boss.
Isotope, baby.
Isotopes.
Here's a picture.
I've seen this before.
Yes.
Oh, back in atomic theory.
Ah.
Oh, it's all coming back
Around. Full circle.
Oh, yeah. Like an atom.
One of two or more atoms with the same number of protons but different masses. That means we have different numbers of neutrons.
Electrons we're not counting because we're not talking about ions.
Right.
But it's the same protons, different neutrons, but still the same element.
Because of the same number of protons, protons are king.
Yes.
Radioisotope.
Radioisotopes. They're not on the radio. That means they're radioactive. They're either natural or artificial, but that particular isotope, that version of that element is unstable and is therefore radioactive, and we call it a radioisotope. Some isotopes are not radioactive. They are not radioisotopes. Some are.
Right. So isotope, the first one is kind of like the overall overarching definition of what an isotope is. This second one is more along the lines of what we're actually honing into with nuclear chemistry.
Exactly.
Okay. Radioactivity.
Wow, a lot of stuff going on.
Yeah,
I see Greek sorority letters. What?
Yeah. So beta, gamma, alpha.
There you go. Those are Greek letters.
Yes, they are. And then we're going to use those and figure those out. So this is the emission of radiation or particles caused by the spontaneous disintegration of atomic nuclea.
See what he did there? He sounded it out and he got it right.
That's a big old word, dude.
One syllable at a time. You'll get every one of them right.
Phew.
Yep. Right. Radioactivity.
Yeah.
Nucleus falls apart and releases something.
Because it's unstable.
Exactly.
And we're going to find because there's just so much stuff in there.
Nuclear stability, on the other hand, is actually a ratio. There's a perfect prime ratio of protons to neutrons that for some reason keeps the nucleus together. When the number of neutrons starts to change, that nucleus becomes a little bit unstable sometimes and can cause the nucleus to spontaneously disintegrate, fall apart, release radioactivity, aka radiation.
Yep.
There it is.
Nuclide, which is a weird way to say that word because that looks like nuclide.
It's both.
I've only heard it's pronounced nucleide. I don't see the E or the I only see the ide.
Anyways.
But this is the atomic species characterized by its contents of its nucleus, hence its number of protons and neutrons.
AKA a particle. Nucleides are particles. Nuclides are particles that will undergo transmutations, disintegrations. That's what it means. When we say it, we're talking about particles that have protons and neutrons.
Yeah, parts of the nucleus, if you will.
Yeah. Sweet. Let's talk about conservation of mass. Big concept in this unit. It's very simple. We've done conservation of mass when we've balanced equations to find the number of each type of atom, but now we're going to balance equations using conservation of mass to show that the mass of the reactant particles, or the parent nuclei, is equal to the mass total of the daughter product particles, to make sure that nothing really went missing in a transmutation.
And that picture was perfect because that's how our nuclear balancing is going to work.
That's how our practice is
going to be able to figure out what the emission is or what the daughter is.
It's the simplest type of algebra you can do.
It really is. And it's nice. A natural transmutation is specifically anything that is going to emit radiation naturally.
Yes.
And so we're going to see there's only one reactant. There'll be two things on the product side. I don't have to force this thing to happen.
It just does it.
It just does it all by itself. Generally, what ends up happening is that nucleus has got so much stuff in there, it can't hold it all together, and it just falls apart. Right?
Now, an artificial transmutation is when we human beings cause the nucleus to fall apart. And we can do that by bombarding nuclei with neutrons and beta particles.
Alpha particles.
We can do that. And the key thing here is that you've got two reactants.
You see in the picture now.
And more than two products usually. Sometimes it's three, but I think all our examples are just two. So artificial means man can force it to happen. Natural means it's just doing its thing all the time.
All by itself. That's basically the sum of it.
Yep.
Correct. We need to be able to pick them out differently. If I give you equations, you need to be able to tell me which one's artificial and which one's...
Ooh, an animation.
golly gee, let's give
Fission.
It's a slow animation, so
Unstable.
we can see it happening.
Oh, okay.
That was an artificial
Transmutation.
that we bombarded it with that particle. Here it comes again, and we're not going to watch it all again. And it's split into multiple things.
The important thing to remember is that fission is a heavy nucleus splits into lighter nuclei.
Right.
Maybe 2, maybe 3, maybe 4. Big heavy atom that's unstable breaks apart into smaller atoms that are more
It
stable.
literally gets cut by something else.
Mhm.
And if we aren't so good with fission, we can use fusion. So we know the word fuse means to put together. And this way, fusion actually is the same thing. The right thing is take two things, put them together, and make a bigger thing.
Hey, you
So
remember when we
combining
did that Super Saiyan fusion? When we combined our videos, we had that sweet animation.
Oh, yeah.
When our powers combine,
Yeah.
you get a bigger, heavier nucleus. We call that fusion.
That is.
Alpha particles are really simple. They're the heaviest and most massive and most charged type of radioactive emission. 2 protons and 2 neutrons. So its mass is 4 AMUs
Yep.
and has a charge of positive 2. We'll see that matters later on.
Yep. And it's basically, guess what? The helium nucleus.
Yes.
That is what a helium is. So the helium nucleus is considered an alpha particle.
It's been stripped of all its electrons because it's got such high energy and it's traveling so quickly, but that's what it is.
That's what it is.
Interchangeable.
Yep.
Beta particle, not the type of fish you got on the kitchen counter.
Nope.
A beta particle is another type of radioactive decay. It's the loss of a high energy electron. So the nucleus spontaneously generates one of these things. I'm not precisely sure how, but it happens. And it is equivalent to an electron.
Yeah, I think it
No mass, -1 charge.
yeah, it has something to do with protons and
Neutrons combining or something like that.
one to the
If
other.
you want to know specifically, let's
We'll
have a
look it up.
discussion.
Yeah, we'll look it up. So we get it exactly right.
There's our electron again.
Guess what? We know what electrons are. Electrons, in this case, though, are
Beta
beta
particles. Mhm.
So in nuclear chemistry, we consider electrons and beta particles interchangeable.
Exactly.
These aren't necessarily, we're not going to deal with electron levels and all that stuff like we did in atomic structure.
All the atoms we're going to be looking at we're ignoring the electrons.
Yeah, mostly.
A positron emission is interesting. We've never seen this before, but it's a positively charged electron.
Yes.
So it's got 0 mass and a +1 charge.
Yep. You'll have that weird B with the tail, but it'll have a plus sign instead of a negative sign.
Exactly. Proton.
Protons are king.
Yep.
Right in the nucleus. Right. They have the mass and a charge.
Right.
That's why they're king. They got them both.
Mm-hmm.
Positively charged particle.
Yep.
Fundamental constituent
Of the nuclei.
of a nuclei.
And we're covering it again because we're going to be working with changing the protons in an atom
Correct.
when we do a transmutation.
Right.
Neutrons, well, that's the other part of the nuclide. It's the neutrally charged particle that has a mass of 1.
But no charge.
And it determines if the element is an isotope or not. So it is really important in this unit because it helps discerning our stability.
Correct. Gamma. This is the boogeyman.
Yeah.
Because you see in the picture that not much changes except for the star.
Mhm.
So it's this high energy, most penetrating radiation. No change in atomic number or mass happens.
Mhm.
This stuff is so powerful. You need a lot of lead
To protect you from it.
keep it from going.
That's the type of radiation that can cause damage to your cells
Yes.
really, really easily.
It's actually coming from the sun. All
I mean,
the time.
they all can, but that one's really hard to stop
That's the
and protect yourself again.
half-life.
That's the decay curve. Every half-life decay curve will look identical to this one.
Yes.
So it goes from 100% to 50% to 25%, et cetera, et cetera, et cetera. But half-life itself is the amount of time it takes for half of the atoms in a current sample to decay.
Yes.
If I had one atom in my hand, I would not be able to tell you precisely when it would go through a radioactive decay. But if I had 10 grams of atoms in my hands, I could say, okay, half of this will decay in the next period of time. You can't predict single, but you can predict
And this
bulk.
is a very important point. It's a holistic thing. I don't know which atoms in that mound are going to decay when, but I know holistically that half of them will decay
by this time.
by that time. That's it. And it's that simple. Here is a picture of basically all
Radioactive decay modes.
the right. We got a lot of them. This is the process.
Nucleus unstable, loses energy by emitting radiation, particles, beta particles, gamma rays, alpha particles, gamma rays,
This is
positrons.
all of them.
That's what it is.
This is a generic word, right? And guess what?
That's all, folks.
Study, take your quiz.
Don't
Peace out.
wait till too late.
No.
Sip.